because some of our other detectors don't give us such nice pictures as we get in figure 6.8, which is showing you a comparison of the gamma spectrum energy resolution of inorganic scintillation versus semiconductor. So you can see that there are two gamma peaks here, and one of them looks kind of like, well, I'm not even drawing it with the degree of sharpness that they're showing you in the book, but one of them kind of looks like this. And the other one looks like this. And this is nice because you can read along here and you can see very precisely what the energy comes to a nice peak here. And then you look at the other detector, which is the inorganic scintillation detector, and you find that that looks kind of like this. This is shown with a dotted line, and it looks sort of like that. And you get these two very, very broad peaks. So in terms of resolution, we'd like to see these sharp peaks. So that's an advantage of using the semiconductor detectors. As you might expect, probably the better the resolution, the more expensive the device is going to be. So in case you were wondering why we don't just always use those kinds of things, sometimes it becomes prohibitively expensive to do that. Now there's another kind of detector, which is called a thermoluminescent detector, which is also an interesting kind of thing. There's again, these are various inorganic crystals. Lithium fluoride and calcium fluoride are frequently used, and these are doped with manganese. And what happens in this situation is that when these things react with ionizing radiation, they actually store the energy, and you can actually get the energy, you can actually get it stored internally inside the crystal. And then it will actually, the crystal will remain in that state for very extended periods of times, many, many months. And you could actually take this thing and then send it off to a laboratory somewhere, and basically they have the technology, they will use the technology to release that energy in a special device in a darkened room, and that will produce, they'll actually start heating this up, and at a certain temperature this thing becomes thermoluminescent. So when it reaches a particular temperature, it's actually going to release photons which can be recorded. So this is that's how these thermoluminescent detectors or dosimeters work. So again, this would be the sort of thing that you would wear if you were working again in a probably not in a nuclear plant, but if you were working in an area where so unlike the pocket dosimeters that we talked about before, these are like little badges that people would actually wear, where there's lower levels of radioactivity, but you still want to know how much of a dose that you're getting. And again, they would be sent off to the lab. Now, the most sophisticated kind of detector that we have here is something called a gamma spectrometer. And gamma spectroscopy is kind of interesting. So this is using a detector to collect both count and energy information from X-rays. So this is very, very, when we're dealing with X-rays, we actually want to be able to, when X-rays fall on other kinds of materials, or gamma rays fall on other kinds of materials, we'd like to be able to get a spectrum of the radiation that's actually produced, such as, for instance, when cesium-137, the stuff that's on the side of my Geiger counter here, when this material is actually, let me close this up, when this material is actually giving off gamma radiation, we could actually read, using gamma spectroscopy, we could actually read the energy of the photon, of the gamma photon that's being produced by cesium. And what we would see is something that looks like the picture that's on page, let's see, the picture that's on page 108, and this is figure 610. So you'll notice that there so this looks sort of like this. We've got a huge peak here, gamma peak, and then there's a little bump here, and then there's something that goes down like this, and then another big peak here. All right, now we know, and this is actually labeled with kilo-electron volt energies. We could change it to million electron volt if we wanted to, but so there's one here that's at about 600 and well, maybe it's around 700. I can't really tell from the scale. Maybe about 650 or 675, somewhere around there. KeVs, that would be 0.67 MeVs. This is the signal for the photoelectron. This is called the photo peak here for the emanation that comes out of the cesium-137. So it's the gamma. If you look on page 108 at figure 611, you'll see that there is well, actually you're having energies here. So there's a beta particle that's produced initially. Then that cesium-137 decays to a metastable barium isotope, and then that gives off a 600. I said 675. It's actually 662. I was just trying to read it from the scale, but it's a 662. So or 0.662 MeV photo peak. And so that's the photoelectron that's being produced by that. There's a couple other things. This doesn't go back to a straight baseline, but it kind of is. If this is the baseline here, there's kind of a sort of a, it comes up a little bit and it plateaus off here. So what all of that is, this is all due to Compton scattering. So there's Compton scattering that's occurring here, and right here we could actually calculate what the maximum energy of a Compton electron would be, and this is called the Compton edge. And Compton edge, the energy is not, let me see if we actually have the energy listed here. I'm not sure whether it's in here or not. I just want to see if this, yeah, okay, we actually do have that. So the Compton edge actually is at 0.478 MeV. So this is 0.662. This is 0.478 MeV. Now, because resolution isn't all that great, and there are some other effects that are occurring, you don't really just have this fall off directly to zero, but it sort of plateaus off and then it goes back to zero. Then we see the photo peak. There's also another peak that occurs at, let's see if I can find the energy for that one. There's another peak in here that occurs at, all right, the other peak is a backscatter peak. And I don't see, I'm looking in the book to see if they actually give us, oh, okay, yeah, it is in here. It's a 0.184 MeV. So this little peak here is the backscatter peak. So that's where the photon is actually scattered back 180 degrees. We see that. But then there's this big peak here that isn't accounted for. And what that turns out to be is actually a peak that is due, this is actually an X-ray that's produced from that excited barium, the barium-137 metastable, as it decays, is giving off an X-ray. And that is, the energy on that one, I don't know if that's that's in there or not. That occurs at, well, it may or may not be in the book. I don't see it right off. Let's see. It doesn't. I don't know. It doesn't. I don't think it says what it is. But that's the point. Point is that is from the barium. So this is the barium X-ray right here. So that's how you. This is typical of what you would see in a gamma spectrum. You'd see the photo peak, which is actually from the principal gamma ray that's being produced from Compton scattering. We'll see the Compton edge. We'll see the backscattered, the backscatter peak, and in this case we get the barium X-ray as well. And you can actually look for various kinds of isotopes. You know, we can look at a decay diagram from that, and we could probably predict, based on the decay diagram, what kind of peaks we would expect to find, and where we would actually find the peaks is something that we could calculate, because if we look at the backscatter peak, and if we look at the Compton edge, and we add the two of those up, that will actually give us the energy, the original energy of the photon. So it's we have the equation in here, which is basically that the E sub 0, which is the original energy, is equal to the energy from the Compton electron plus the maximum Compton electron energy, which is the Compton edge, plus the energy of the backscattered photon. So we can actually, I think there's an example in the book where they actually do this as a problem, and see if I could find that. So, well, if you take the, let's see if that's true. So if we take the 0.184 and we add it to the 0.478, that should give us, yeah, that gives us 6.6. Yeah, it actually comes out to exactly 0.662. So that, if you add this one and that one, that will give you the energy of the photo peak. So that does work. We've also got a couple other formulas in here. I don't expect you to know these, to memorize these. One of them says that we can actually find out the energy for the Compton electron by taking the photo peak energy, squaring that, and then dividing it by E sub 0, and then adding to that, dividing it by the quantity E sub 0 plus 0.2555. That's equation 6.1. If I asked you a problem like this on the exam, I would give you the equation. I don't expect you to memorize this particular equation, although you should know this equation, but I don't expect you to memorize either 6.1 or 6.2, which is a way of finding the backscatter energy, and that is equal to E sub 0 over 1 plus 3.9 times E sub 0. So again, both of those equations, you should just be aware of how to use them, but you don't actually have to memorize them, because if I do ask you a question, I'll actually give you the equation. It'll be in the problem. There's another peak that we sometimes see, which occurs when there's a low energy gamma photon that's emitted, because these things are going to be using detectors that have the detectors in here are going to be iodides. Sometimes these particular iodides will actually react with these low energy photons, and we'll get a K alpha X-ray that's produced, and the K alpha X-ray has an energy of 28 kiloelectron volts, so that would be a 0.028 MeV X-ray, and this is called an iodine escape peak. So that would be, if there were one of those, it would be way down here. This one doesn't show it, but we sometimes see that. I think there is an example here that shows an iodine escape peak for, let's see, for is that cesium 57? Yeah. So on cesium, we were looking at, not cesium 57, what is that? Cesium, it can't be right. Cobalt 57, I'm sorry. Low levels of light here make it very hard for me to see. So that's cobalt, we've got a cobalt 67 photo peak, and right next to that is this iodine escape peak, which is actually that iodine X-ray that's being produced from the cobalt bombardment. So you got the big cobalt photo peak. This gamma actually causes excitation of the crystal, and you get this small peak here, which is the iodine escape peak. So that's another peak that you will sometimes see in gamma spectroscopy, and it's important to be able to recognize these things if you're actually using this technique, because if you don't see that, you can waste a lot of time trying to figure out, well, is this some impurity that's in there? At least you know, once you are able to identify what the various kinds of peaks are in there, and you can usually do that from the shape and from just the energy differences, because we know that this is going to differ by this peak will differ by that peak, from that peak by a certain energy, and that this peak will actually have a particular energy, this what did I say, 0.02, what was the energy? Yeah, the 0.028 MeV X-ray, so that we would know that that would always come out at exactly the same position in this kind of a spectrum. Okay, so the other things that you also will sometimes see are what are known as an annihilation peak, and of course that's from positron annihilation. Positron encounters a beta particle or an electron, and it annihilates. And where this happens, where the annihilation actually occurs, whether it occurs inside the detector or outside the detector, is going to make a difference in how this is actually going to be observed. So we're going to have gammas with energies greater than 1.022 million electron volts. We saw that last week. This is typical in the decay of something like sodium-22. So this may undergo something called pair production, which is basically, you know that if you've got a very energetic gamma, that the gamma itself can actually go to a positron and an electron. So depending on where that actually occurs, whether it occurs inside or outside of the detector, that's going to very much influence how it's actually observed by the detector. So if the pair production occurs outside the detector, the positron is going to be annihilated outside the detector, and what you're going to get is a gamma that's going to go back inside the detector, and you're going to get a gamma that's going to have an energy of 0.511 MeV. That's for one that actually occurs in that way. And then there's another possibility if pair production occurs inside the detector. So there's two possibilities. If that actually happens, there's two possible scenarios. In one case, one or both of them may actually escape, and the energy will be if the electron escapes and not the positron, or if they both escape, we're going to see what's called an escape peak, or if both of them escape, we're going to see something that's called a double escape peak. So the peak that is 0.511 MeVs below the photo peak is called the escape peak. So if this were the photo peak, and then we measured down 0.511 MeVs in this direction, we would see an escape peak. And if we had if both of these escape, then we would have what's called a double escape peak. And so you might see a situation like this, which is the single escape, and then at the same, another 0.511 down the road, you'd see another one there. That would be the double escape peak. So those are other possible things. And you actually see that. The single escape peak is, the probability is greater, so you're going to see a larger peak for that. I didn't draw that, really should be like that. So for instance, I think that might be, is that sodium? Doesn't tell us, it doesn't tell us what element we're dealing with, but basically we've got a photo peak here, a single escape peak here, and a double escape peak here. And this is a gamma spectrum for that kind of material. Could be something like, as I said before, it could be something like sodium-22 that's doing that. Yeah, it's unfortunate that he doesn't label these in the book as to specifically which isotope that's being dealt with, so I don't really know what that is. But anyway, what I'm referring to is figure 618 on page 114. So that's the gamma spectrum with the escape peaks in it. And then finally, the last thing, or the last two things in here, are something called the, there's one here that's got a couple other things that we haven't looked at. One of them has, actually the only thing that's different in this, and again, I don't think it tells us what the, I'm just looking here. It may be that this is referring, that this actual figure 619 is probably referring to the decay of this rubidium isotope, and it is rubidium 86. So what you see is you'll see a Compton edge, or the whole Compton continuum. So you've got something that looks sort of like there's actually a little kind of a dip down here, but then you have like a little bump here and kind of something that looks like that. So this is all Compton scattering here, but Compton scattering is actually preceded by a very large rise here, and all this here is due to Bremsstrahlung. So when you see that kind of a thing, that's very, very typical of Bremsstrahlung. And Bremsstrahlung, because there's so many energies associated with it, it's just a continuum of different energies of X-rays. So that is probably the last part of this. There's one other thing in here. Let's see. Oh, it also talks about, your book also talks about the fact that that the gamma photons can undergo Compton scattering while traveling through an object on their way into the detector. And this is called object scattering. We don't actually see this in here, but object scattering is something that can occur, and this could be anything that's in the way of the between the photon and the detector. Anything could actually wind up scattering that photon. So it's at least the more counts under the Compton continuum than you would see if you didn't actually, what object scattering is doing, it's making this bigger, but it's actually making the photo peak smaller. So if there's a lot of object scattering, obviously you want to minimize object scattering because that's going to give you a falsely low value for your photo peak. And there's one other term that's in here, which is the peak to total ratio, which is just a way of measuring it's a way of measuring what the quality of your detector is. So you'd actually like to see the highest peak to total ratio, because the peak is what we're talking about, is the ratio of the photo peak to all the other stuff that's in here. Because everything else that's in here is really just taking away from the photo peak. So a better system would give you a larger ratio. Okay, so that really concludes this particular presentation, and we're going to start next time with a chapter on nuclear reactions. Thank you again for your attention on this very lengthy presentation, but as I said, we're going to at least take one portion out of it, which will be the demonstration part.